All right, so we're talking, like was just introduced, we're talking about how Kubernetes components in your cluster communicate and how they do that securely. So welcome, my name is Kaczorowski. I'm a product manager working on container security at Google. Recently, I've been thinking a lot about the certificates that you have in Kubernetes and the roots of trust that you depend on in your cluster. I initially didn't know a lot about this, so I wanted to do some research and learn a couple of things, and that's what we're talking about today, what I've learned. So in this talk, we'll talk through how Kubernetes components communicate within your cluster and the security of these communications. First, we'll cover what the main components are and what communications go between those components. Then we'll talk about what communication security should be and like the properties that you might want and how this is typically implemented. We'll talk about the certificate authorities that exist in Kubernetes and how these are used to protect cluster communications. And then we'll wrap up so that you understand how all these pieces work together in concert. All right, so first off to start, what components of Kubernetes even communicate with each other? So here's your cluster at a high level with the main Kubernetes components. On the left in the control plane, you run several pieces on master nodes to actually control your clusters. The Kubernetes controllers, which tell your clusters what to do, and etcd, which is a database that stores your cluster state. On the right, in your worker nodes, you run your workloads. There are Kubernetes components there deployed on your nodes that are needed to actually manage the workloads. These listen to the Kubernetes controllers that are in the master and do what they're told to do. And your workloads themselves. The worker nodes run your pods, which are just collections of one or more containers. So if we break down these components a little bit more, you can break down on the left the Kubernetes controllers into the API server, scheduler, controller manager, and other controllers. These perform the typical functions that you'd expect of your Kubernetes cluster to scale, schedule workloads, and respond to user requests. You'll also see that we've broken out etcd into more than one instance of etcd. Etcd is a distributed data store and run in a high availability mode, so there are multiple instances that interact with each other to actually maintain state for your cluster. And on the right in the worker nodes, you'll see we have the kubelet, which is the main component on each node in Kubernetes. It's responsible for what's running on that particular node and receiving instructions from the control plane. It watches the containers and makes sure they're running as they're supposed to be running. And other Kubernetes components, like kubeproxy or kubedns, are actually run as daemon sets, which are pods that must be run on every node in your cluster. This could also include other system containers or add-ons for your particular configuration or from your cloud provider, for example. So for things like logging and monitoring. kubeproxy is a little bit special in that it's also how admins can access the worker nodes directly, and it also talks to the API server to keep the network configuration up to date. So if we add the flows that actually go between these components, you'll notice, and don't worry, we're going to keep this relatively simple, that some of these components actually seem to get a lot more attention and act as the flow-through points for a lot of communications that exist in your cluster, including between other components. And specifically, you'll see that almost all communications touch the kube API server, the kubelet, and etcd. For example, say your pod needed a secret. It would tell this to the kubelet. The kubelet would communicate this to the kube API server, and the kube API server would communicate with etcd to actually retrieve that secret. So the kube API server is critical for everything in the cluster. Admins talk to it, other Kubernetes controllers talk to it, etcd talks to it, and it's the point of communication with the node's kubelet. All communication paths from the cluster to the master terminate at the API server. Similarly, everything that goes from the node goes through the kubelet. It's the brain center for the node. And etcd is critical in that it stores state. So it holds all the important info with your cluster. It acts like sort of like a hard drive for your cluster. So even if it doesn't talk to many other pieces, we're going to want to make sure any communications with etcd are really well protected. So with that in mind, we're going to focus more heavily on these three pieces in intra-cluster communications: the kube API server, the kubelet, and etcd. Okay, but first, let's talk about properties of good communication security, and we'll come back and then apply that knowledge to Kubernetes. So when protecting data in transit, there are three common security properties you're going to want to look for. The first is authentication, which ensures that you know and verify the source and destination of the communications, whether it be a human or a process. You're verifying that the correspondents are each who they actually claim to be. Integrity, which makes sure that the data that you send arrives at its destination unaltered. You're verifying that the data hasn't been tampered with and also hasn't been falsified. And encryption, which protects your data by making it unintelligible while in transit in order to keep it private. Encryption is the process through which legible data, known as plaintext, is made illegible, known as ciphertext, with the goal of ensuring that the plaintext is only accessible by parties authorized by the owner of that data. And the algorithms used in the encryption process are well known, but the key required for decrypting the ciphertext is kept secret. So encryption in transit often uses asymmetric encryption for key exchange to establish a shared symmetric key, which is then used for the actual data encryption. Note that some forms of encryption actually already have integrity and authentication as part of the encryption, so there aren't necessarily separate systems that you're putting in place. You might be able to get many of these characteristics for the price of one. And we can expect different kinds of communications between components in our infrastructure. There are client-to-server communications, where a client like Alice is a user requesting a web page, for example, and connects to a server like Bob, which receives the request. You can also have peer-to-peer communications, for example, when running a system in high availability mode, when there are several nodes of the same service up and running. The peer nodes are going to want to mutually authenticate to ensure that they're in fact equally trusted. This just means that each node needs to act as both a client and a server in that peer state. So suppose Alice and Bob are communicating, and they're encrypting their messages to each other. If they communicate using transport layer security, or TLS, Alice and Bob perform a handshake, and Alice knows that she's talking to Bob because she can verify Bob's certificate. Mutual TLS means that both the server verifies the client's identity and the client verifies the server's identity. But if Alice hadn't authenticated Bob, their communications are subject to what's known as a man-in-the-middle attack. A man-in-the-middle attack, or a person-in-the-middle attack, or a monkey-in-the-middle attack, whatever you want to call it, occurs when another party can intercept and relay all messages between the two parties who are trying to communicate. So Eve, the eavesdropper in this case, pretends to be Bob when talking to Alice, and pretends to be Alice when talking to Bob. And every time Alice sends a message to Bob, Eve intercepts it and can read it before sending it on to Bob. We also have malicious Mallory might even change the content of that message if they wanted to. The worst part is Alice and Bob actually think that they're talking to each other. They have no idea. That's why authentication here is so critical. However, even with authentication, we face a slightly different issue, right? How does Alice know that Bob's certificate is really Bob's? Suppose, for example, that Eve has a certificate and she just signed it with Bob's name. How would Alice know any different? And this is where a certificate authority, or a CA, comes into play. A CA is an entity that issues these digital certificates, and it's responsible for verifying the identity of the entities to which it issues those certificates. So a CA acts as a trusted third party in that system, in that it's trusted by both the owner who owns the certificate, like our server Bob, and it's also trusted by the entity which is relying on the certificate to be true, like our client Alice. CAs are chained so that more easily managed CAs are actually used for day-to-day operations. So a root CA signs a root certificate like you see here, which can then be used to sign intermediate certificates, which can in turn be used to sign leaf certificates. In practice, a root CA is one that's widely trusted. This allows users to ultimately only trust a handful of, a very small number of parties, the roots, in order to be able to protect their communications and rely on things that are below those roots. To get a certificate, an entity generates a key pair, then the entity submits a certificate signing request, or a CSR, to a CA, which contains the public key and the entity's identity, and that's signed by the CA. A self-signed certificate is a certificate which is signed by the same entity to which it's issued. So note that specifically a root certificate is actually a self-signed certificate, but we place more trust in it due to who manages it and some of the processes they might have in place to actually manage those keys. A really important item to call out here when we're talking about Kubernetes is the difference between public web CAs and private CAs. Right? A public CA is used to authenticate websites that you connect to on the public internet and has root certs from a handful of trusted CAs. Those are usually shipped with like your browser or your device. And these web certs need to come from a public CA, whereas a private CA might be used within an organization, for example, between components in your infrastructure. Kubernetes uses a private CA for components, and you'll need to use a public CA for any web apps that you host on Kubernetes, for example, that you want web end users to connect to. And when we talk about public key infrastructure, or PKI, we're actually talking about all of this stuff. We're talking about all these systems in your organization, the CAs, if you have any, what CAs you trust, your private keys, your certificates, how you manage the keys, all of that stuff. It's how you organize that entire infrastructure. Each organization's needs here are going to be very specific, so that how you set that up should actually be dictated on your needs, rather than me telling you what's the best practice in that regard. One last item I want to cover to avoid confusion is between keys and certificates. When you generate a certificate, you first need to generate that asymmetric key pair, like I just mentioned, with a private and a public key. Your public key verifies who you say you are, and you can use that to have people send you messages, whereas your private key is how you prove who you are using signatures, and you can read your messages using decryption. You make your public key, well, public, right? But to verify that it's in fact your key, like we were talking earlier about Alice and Bob, it's signed by a certificate authority. The certificate authority uses their private key to sign the certificate, effectively saying, yes, I attest that this is Bob's key. Then the entity examining your certificate, like Alice, only needs to verify and trust that signature in order to believe that it's in fact your public key. So going back to earlier, though, with a self-signed cert, the entity, it's just an entity that signs their own public key with their own private key, right? That's what a self-signed cert is. It's the same entity that's doing both. Okay, so now that we have some PKI basics covered, let's dig into specifically what happens in Kubernetes. Lots of people have complained to me that setting up your Kubernetes CA is really hard, and it's one of the hardest things to do if you're running Kubernetes yourself. It's one of the first steps that you take, and it's critical to your cluster security, so you really want to get it right. But do you really understand what you should be doing? So if you're using something like a hosted solution that's often managed for you, or if you're using kubeADM, also automatically generates the certificates that you need. So rather than digging into how to generate certs, I'm going to talk about what the certs do and what they protect. When you're setting up your cluster, if you do it yourself, for example, following Kelsey's Kubernetes the hard way, you're going to need to generate the CA config file, certificate and private key, generate client and server certs for all the components, the appropriate components, and distribute the private keys and certs to all those components by copying them into the master and worker nodes respectively. That's actually a lot of work. If you use kubeADM, then the certificates that your cluster requires are automatically generated. Similarly, if you use a hosted solution like GKE, this is done for you. An alternative is actually not to have your cluster or a setup tool create, manage, and install any of the keys for you. That might make sense for a situation where you have a CA that you run outside of Kubernetes, and you just want to import the necessary certificates to your cluster. That lets you rely on an external root of trust. You can also use kubeADM in this case. It's a functionality called an external CA in kubeADM. If you are doing this, the root CA can be outside Kubernetes, but you still, at minimum, need some intermediate CAs that Kubernetes manage, right? The root's there, and it signs things that the intermediates use. Kubernetes actually needs at least 2 CAs to operate. The Kubernetes cluster CA, sometimes called the cluster root CA, and the etcd CA, and optionally, or slightly differently, the kube front proxy CA. Since this allows routing from the public internet, you'll actually need that to serve public certs, so it's an O category, and we're not gonna cover it now. You can root the cluster root CA and the etcd CA in a single CA, like an external CA, like we we're just mentioning, but you don't need to. That's actually what's assumed in the Kubernetes documentation. As mentioned earlier, though, you should set up your cluster certificates in a way that meets your organization's needs. These CAs issue certificates for various Kubernetes components, the ones that we discussed at the very beginning, in fact, for client and server certs for the kubelet, API server, and etcd. So what does that actually look like? Here's a quick summary of which bits have the certs that we just talked about. The kube API server has a server cert and a client cert so that I can talk to the kubelet. etcd has a peer cert and a server cert, and client certs to talk to the API server and the etcd health check client. And the front proxy client has a server cert. Your kubelets are also going to need certs, but those aren't actually part of that initial setup. I'd also really recommend checking out the Kubernetes documentation here. There's a really nice table on all of these certs, including what they're signed by, if they're client or server certs, and where the certs actually live in your cluster. The etcd certs and keys, like no surprise, live in etcd. So this was still a little bit confusing to me when I was learning this. I was like, I think of a CA as being online and something I can just like send requests to and make things happen, right? Like, and just sign stuff. So now that I know where all the certs and keys are stored, how do I actually sign things? And that's a certificate signing request. So that's when a component goes to a CA and requests a cert signed for itself. If you think to our Kubernetes components, when and why would that actually happen? Well, very commonly, it would happen when a new node joins a cluster and the kubelet needs a kubelet cert to talk to the API server. So luckily, Kubernetes provides a certificates API, which lets you provision TLS certs signed by a certificate authority that you control. This allows for certificate signing requests, or CSRs, and so this CA and certificates can be used by your workloads to establish trust. This feature's in beta in Kubernetes. Note, however, that the Kubernetes certificate authority doesn't work out of the box. You can configure an external signer to be used with this, or you can use a built-in signer and tie it to an existing CA, such as the cluster root CA. That's a fairly common setup. To activate the built-in signer, you have to pass the cluster signing cert file flag and the cluster signing key file flag to kube controller manager. In the design to take the certificate signing request to stable, there's also a proposal to allow multiple CAs. So if that's something you're interested in, please go comment on GitHub. So to use this API, first you have to create a certificate signing request. It's a file with a particular format that is used to meet PKCS 10, and you can generate it using a tool like Cloudflare SSL or CF-SSL. Then send the request as an object to the API server to trigger the Kubernetes certificate signing request. You can then also check its status in the API server. And then, and this is the critical bit, you need to get the certificate signing request approved. This is either done manually, like by an admin, or it can be automated. If you've configured an approver to meet certain criteria automatically, that works well. I really say that this is critical because this is effectively delegating trust for your entire cluster. Or anyone or any system that can approve these requests is able to decide who can be in your cluster and how they can talk to each other. The approver needs to authenticate the client asking for the cert and be really stringent in validating that request. And you should only grant those permissions carefully. And finally, once that CSR is approved, you can download the certificate, distribute it to the different components that need it, and then use it. You can also configure certificate rotation for these certs. Your kubelet certs are valid for 1 year by default. That means that they have a 1-year expiration so that they don't have to be renewed too frequently. And also because your nodes are probably going to change anyways, right? Like cattle, not pets, right? To check the validity of a certificate in kubeadm, you can check expiration with an appropriately named flag. To renew your certs, well, kubeadm also takes care of this for you. It will renew certs as part of a control plane upgrade. It's not recommended to only rely on this, however, if you have more complex needs. But if you're regularly upgrading anyways, and you should be, then this is an okay solution. You can also manually renew certs by explicitly triggering a renewal with kubeadm certs renew. To renew certs using the certs API, just specify use API as part of the request. And if you want, you can also just generate the CSRs yourself, like if you're using external CA, or you can also just renew single certs. It doesn't have to be all the certs that you have. And introduced in Kubernetes 1.8 in beta, kubelet cert rotation allows you to set an automatic rotation period, which is even better, at which point a new key will be generated and a new certificate requested before the current cert expires. Once a new cert is available, it can then be used to authenticate connections from the kubelet to the API server just as it was doing before. So to set this, pass the kubelet process a rotate certificates flag, which will cause it to request a certificate when close to expiry, and pass the kube controller manager an experimental cluster signing duration flag, which controls how long the certificates are used for. Again, something like a year is reasonable, but it really depends on your environment in this case. So now that we get how the certificates and the certificate authorities in Kubernetes work, let's figure out how the communications that you have are protected. Going back to our diagram, I want to highlight a couple of flows through the API server, kubelet, and etcd that we're going to focus on. 1, from the API server to the kubelet. 2, from the kubelet back to the API server. 3, between the API server and etcd. 4, between 2 instances of etcd. And then 5, from an admin to the API server. So let's go into each of these one by one. So first, from the API server to the kubelet. The API server might communicate with the kubelet to fetch logs, attach to running pods, and provide port forwarding. By default, in Kubernetes, your connection from the API server to the kubelet is protected with unauthenticated TLS. These connections terminate at your kubelet's HTTPS endpoint. The API server does not verify the kubelet's serving certificate, which makes the connection subject to person-in-the-middle attacks, and therefore unsafe to run over untrusted networks. This might be fine, right? Like, for example, if you're running all of this on your own private network, that's not necessarily a concern. You can force authentication here if you want to, using the kubelet certificate authority flag with the API server so that you specify a root cert bundle, which is then used to verify the kubelet server certificate. You can also use SSH tunneling to avoid connecting over an untrusted network. However, SSH tunneling is actually deprecated in Kubernetes and doesn't address the actual authentication issue, so maybe not the best way of solving that issue. No matter what, you still verify authorization for requests to the kubelet API. For other node components, from the API server to nodes, pods, and services running on that node, the connection uses plain HTTPS connections by default. They're not authenticated or encrypted, but actually those communications shouldn't really be happening anyways. But if you are for some reason doing that, you can specify an HTTPS endpoint to encrypt the connection, but that still doesn't validate their certificate, so there's no authentication or integrity for those flows. Okay, let's go in the reverse direction. From the kubelet to the API server, a kubelet will communicate with the API server to watch for pods that it's supposed to run and report its own health. The API server listens for connections on the secure HTTPS port 443 for connections from other master components, from the kubelet, and from admins. So from cluster components to the API server, requests are over TLS. There are many kinds of authentication to the API server available, and you can enable many of them, but including specifically a mode called node authorizer, which is meant for these requests that are coming from kubelets. The kubelet will use whatever it's specified in its own kubeconfig, which can be node authorizer, or other authentication methods, like if you wanted to use bearer tokens or something instead. In order to be authorized by the node authorizer, kubelets have to use a credential that identifies them as being in the system nodes group. This is provisioned in the kubelet cert, which specifies the identity of the kubelet. When you use node authorizer, this connection is protected with MTLS. Since this connection has authentication, integrity, and encryption, by default, the master can run on untrusted networks, so that's kind of exciting. From the pod to the API server, the pod can use a Kubernetes service account to talk to the API server. When this service account is created, Kubernetes automatically injects the public cert and a bearer token into the pod, and the pod is then able to communicate and authenticate to the API server using server-only authenticated TLS, also to the same HTTPS port 443. The client certificates use the bearer token, so this protection also has authentication, integrity, and encryption, which is great. Okay, now from the API server and etcd. The API server and etcd might communicate, for example, to ask for and return a secret for a particular workload. From the API server to etcd, the communication is entirely over localhost, HTTP port 80, and it's not authenticated or encrypted. Now that sounds scary, but it's actually probably fine. These components are in practice running on the same node, so protecting the local connection more significantly probably isn't needed. But if you want to, you can optionally set up TLS and client cert auth to have the API server verify its identity with the etcd server. And to do that in the API server pod spec, just set etcd cert file and etcd key file flags. And then in the reverse direction from etcd to the API server, as I noted earlier, the API server listens for connections on HTTPS port 443, and that includes those master components. So this connection is authenticated and this connection is authenticated using one of the etcd certs. So again, despite being a local connection, and this is not unusual, despite being a local connection, you have authentication, integrity, and encryption, but that's not unusual as all the requests to the API server are authenticated in such a way, or in some way. Now between two different instances of etcd. An instance of etcd might communicate with another instance of etcd to keep state updated, since etcd is a distributed data store. So when an instance of etcd sends a request to another instance, that request is authenticated and encrypted using mutual TLS. etcd uses those peer certs that we talked about earlier, which are both client and server certs, specifying the host identity. And then lastly, from the admin to the API server. Now, the admin isn't one of the three main components I was talking about before, but it's one of the most commonly asked about questions, so I'll just quickly summarize some options that you have here. The admin might connect to the API server to, say, manage the cluster. The admin can also connect to the kubelet, which requires kubelet authentication, but we're not going to go into that. The admin should connect over TLS, but doesn't have to authenticate in TLS, right? There are many different kinds of authentication methods available here, including OAuth tokens, for example, using OpenID Connect, X5 client certs, basic auth using static passwords, an authenticating proxy, and more. So if you're using the client cert method, you can actually set this up using the certificates API and from the certificate signing request API that we talked about earlier. You should ideally pick only one option, or rather as few options as possible, in order to make this as easy for yourself to manage, right? And control the potential authentication surface. Unless your specific application needs a particular authentication method, you should disable it, or rather not enable it. Authentication isn't the only control here anyways. After authentication, there's nonetheless authorization for the admin using RBAC. Note specifically that when anonymous authentication is enabled, requests that are not rejected by other auth methods are considered anonymous requests, and they can still perform actions that you give permissions for. So be very careful about that in your authentication plan. And there are other communications that occur in your system that we didn't talk about, like the kube scheduler and the kube controller manager talking to the kube API server. There's also communications that might be part of your workload or your infrastructure. So a node might communicate with another node as part of a specific workload. There's no Kubernetes components that require node-to-node communication. But when the node sends that request to another node, that request is protected as however you've implemented in your environment. You can also, again, use the certificate signing request API to give these node certificates for authentication if that's what you want to do. And a pod might communicate with another pod as part of a specific workload. Again, no Kubernetes components require this particular pod-to-pod communication. When the pod sends a request to another pod, that request is neither authenticated nor encrypted. However, you can restrict pod-to-pod traffic with like a network policy, and you can encrypt that traffic using like a service mesh like Istio or otherwise implementing application layer encryption. All right, so pulling it all together, how is traffic within your cluster then protected? And how do Kubernetes components communicate securely? In summary, for the 5 flows that we've looked at, 1, from the API server to the kubelet. This uses unauthenticated TLS by default, so your communications are encrypted but not necessarily authenticated. You'll need to specify a kubelet certificate authority and specify the HTTPS endpoints for your nodes. 2, from the kubelet to the API server. This uses mutual TLS by default, so you get encryption, integrity, and authentication. Check mark, we're good. 3, between the API server and etcd. The API server talks to etcd over localhost, which is not protected, but like we said, that's probably okay, and you can set up MTLS if you prefer. And etcd talks to the API server over HTTPS and is authenticated, encrypted, and has integrity. Between 2 instances of etcd, these peer instances communicate using mutual TLS. And from the admin to the API server, you have lots of options depending on your authentication method. Just be careful with anonymous auth. So I work at Google on GKE, and I want to call it a couple of additional optional controls you have there, what might be different from what we just described. By default, GKE sets up the cluster root CA and the etcd CA for you. These are single cluster CAs, so that if any one cluster's private key were to be compromised, no other cluster is affected. Certs are issued by the cluster root CA. Certs that are issued by the cluster root CA have a validity of 5 years. Right now, it's your job to rotate those certs, given that you might have other dependencies on that CA and those certs in your cluster. You can do that by completing what's called a credential rotation, which it creates a new cert, waits for you to update anything that needs that cert, and then completes the rotation by invalidating the old cert. Note that today that also requires a migration to new IP addresses. Starting in GKE 1.13 and higher, the traffic from the API server to the kubelet is authenticated by default. In GKE, the etcd CA is fully managed for you, and Google manages rotation of those certs. There's nothing there for you to do. And the certificate signing request API is also already set up for you and set up to use the cluster root CA. So there's an automated approver that you can use for those certs. If you use an option that we have called shielded GKE nodes, the biggest difference is how the kubelet's bootstrap credentials are protected. That's what's actually used when submitting that certificate signing request. The certificate signing request is bound to the machine identity, which is protected by a VTPM element. So you can't use that shared secret from anywhere but that node. So basically, what I'm trying to say is that no one else can pretend to be that node and go get a certificate for that node. That's actually really powerful. If you're running on GKE, please enable shielded GKE nodes. It's a great security feature and also ensures secure boot for your nodes. And lastly, for user authentication, basic auth and client certs are not on by default in GKE since 1.12, but if you have an older cluster that you've been updating, please disable those for cases where you don't need them. And if you want to read more, check out the documentation on cluster trust that explains how some of these things work on GKE. Some of you might also be familiar with the Center for Internet Security, or CIS, benchmarks for Kubernetes. These were recently updated about a month ago to version 1.5.0 of the benchmarks, which apply to Kubernetes version 1.15. I know that's confusing, the numbers are not the same. You might be using these in your environment to verify that your environment is meeting the recommended best practices for security. So I want to call out some of the benchmark elements that specifically relate to cluster trust and the elements that we've been discussing. For the API server, 1.2.6, you should set up the kubelet certificate authority to verify the kubelet for communications from the API server to the kubelet. 1.2.29, you should set up a TLS connection between the API server and etcd. 1.2.30, ensure that the API server only serves traffic to encrypted HTTPS endpoints. For the controller manager, 1.3.6, make sure to rotate the kubelet certs. And for etcd, basically all the recommendations in the CIS benchmarks are about getting this trust model right. So set up TLS, set up client auth, ensure etcd is only serving HTTPS endpoints, make sure the peer certs are set up appropriately, and set up a separate CA for etcd. 3.1.1 calls out that the client cert auth should not be used for users, instead use OAuth or another such method. And finally, on the kubelet, 4.2.10 is to ensure that the kubelet only serves traffic onto HTTPS, and 4.2.11 and 12 are about setting up automated cert rotation for kubelet client certs. All in all, nothing unexpected here. If you follow the recommendations that we've been talking about the whole time, you'll be in a good spot on the CIS benchmarks. And to give you kind of a one-slide takeaway of the best practices from today, if you have to remember something from this talk, First, set up your cluster using kubeADM if you're not using a managed service that does it for you. This will be significantly simpler for you than doing it yourself, and you can still use an external CA. Please rotate your certs. This doesn't have to be super frequent, but either set this up to do it automatically or do it manually on a regular enough basis so that minimally you know that you can do it, and you can do it if you want to have to do it, if you have to do it in the future. In terms of some of the specific paths that your cluster that are covered, there are a couple of different options, but again, I'll call out the most high impact ones. From the API server to the kubelet, use a kubelet CA to authenticate the API server. And from the kubelet to the API server, use the node authorizer as your authentication option. And if you want to use a CA to establish trust for other components, you can use the Kubernetes certs API. And finally, if you're running on GKE specifically, please use shielded GKE nodes to protect kubelet bootstrap credentials and perform a credential rotation, again, on a regular enough basis so you can rotate the certs in your cluster root CA. So that's it. I have a couple of links here if you want to learn more about some of the stuff that we talked about. And thank you very much.